All right, in this video, we're going to talk about section 5.5, dealing with the fundamental theorem of calculus. And in this section, we're going to evaluate integrals using the fundamental theorem of calculus, and also we'll solve applications involving definite integrals and the fundamental theorem of calculus. All right, so we'll begin with theorem 1, dealing with the fundamental theorem of calculus. Okay. And it says here, if f is a continuous function on the closed interval a comma b, and capital F is any antiderivative of lowercase f, then the integral from a to b of f of x dx will be equal to this, f of b minus f of a. Okay. Now, if you recall in the last video, section 5.4, we were finding the area using a definite integral. So here, we're going to be given pretty much the function themselves, and we're actually going to find out what the antiderivative is, and then find out what that area is when we're given the lower limit and the upper limit. By the fundamental theorem, any definite integral of a function f can be evaluated whenever we can find the antiderivative, capital F, and evaluate capital F of b minus capital F of a for the limits of integration a and b. Okay. Now, antiderivatives of a function f differ by, at most, a constant. When using the fundamental theorem to evaluate a definite integral, we generally choose the simplest antiderivative by letting the constant c equal to 0. All right, so in this case here, in evaluating definite integrals with the fundamental theorem, it is convenient to use the notation f of x, capital F of x, and that will be from a to b. And that's going to represent the change in capital F of x from x equals a to x equals b. That is, of course, capital F of b minus capital F of a. All right, so here, when we're dealing with a definite integral, we don't use the plus c. With the indefinite integral, we do use the plus c. So in these examples that we will cover in this video, we're not going to be requiring the plus c because we're given lower limits and upper limits in our examples. So like in example 1, let's say I want to evaluate the integral from 9 to 10 of 6 dx. The integral from 9 to 10 of 6 dx. So in this case here, we're going to integrate 6 dx. Well, we're integrating the constants, and that means it's going to be that constant where we include the variable itself. So the integral of 6 dx would just be 6x. But here we got our limits of integration from 9 to 10. So it'd be 6x, and we don't include the plus c because we have definite integrals that we're dealing with. So 6x, and then we're going to find out what that area is from x equals 9 to x equals 10. And in fact, when we're finding the definite integral, we're actually finding the area between 9 and 10 in this case. So here's what we do. We're going to do the upper limit minus the lower limit. In other words, we're going to do 6 times the upper limit, which is 10, minus 6 times the lower limit, which is 9. So 6 times 10 will be 60, minus 6 times 9, which is 54. 54 from 60 leaves us with 6. So what that 6 means, that's the area of the curve, or the area of that curve from 9 to 10. Or between 9 and 10. All right, here's another example. So that one was the easiest one. We'll progress to more difficult ones like this one, the integral from 2 to 3 of x dx. the integral from 2 to 3 of x dx. I'm going to go ahead and rewrite this. Well, in this case here, we're going to have to use the power rule for integration by increasing the power by 1 and then dividing it by that new exponent. Because this is like x to the understood 1. So that means if I increase that exponent by 1, it'll be 1 plus 1, which will be 2, divided by the new exponent, which is 2. So it'll be x squared over 2, and it will be from 2 to 3. So we're going to be finding the area underneath that curve, or the area underneath the line from 2 to 3, between 2 and 3. So again, this will be the upper limit minus the lower limit. So the upper limit is 3. So this will be 6 squared over 2 minus the lower limit, which is 2 squared over 2. Well, I'm sorry, this should be 3 squared. The upper limit is 3. And then where I get 6 squared. So that should be 3 squared over 2 minus 2 squared over 2. So in this case here, if I square the 3, that's going to be 9. So it'd be 9 over 2 minus 2 squared, which would be 4 over 2. So if I subtract 4 halves from 9 halves, that would be 5 halves. That 5 halves represents the area of the curve between 2 and 3. All right, example 3. The integral from 4 to 5 of 2x squared dx. Okay. The integral from 4 to 5 of 2x squared dx. Well, since I have a constant in front of the x squared dx, I can pull that out in front of the integral sign. So it'll be 2 times the integral from 4 to 5 of x squared dx. And then 2 times, let's go ahead and integrate x squared dx by increasing the power by 1. So if we add 1 to this 2, it will be 3. So it'll be x to the third divided by that new exponent of 3. And that's going to be from, in this case, 4 to 5. And let me go ahead and simplify this as 2/3 x cubed from 4 to 5. So we're going to be finding the area between x equals 4 and x equals 5. So here, this will be upper limit minus the lower limit. So here, I'm going to have 2/3 times x, which is 5, and that's cube, minus 2/3 times the lower limit, which is 4, so that'd be 4 cubed. Now, if I simplify this, that 5 cubed, that's 5 times 5 times 5, that's 125. 125 times the 2/3 would be 250 over 3. And then minus 4 cubed is 4 times 4 times 4, that's 64. 64 times 2/3 would be 128 over 3. Subtract 128 over 3 from 250 over 3, you'll get 122 over 3. So the integral from 4 to 5 of 2x squared dx will be 122 over 3. That represents the area of this curve between 4 and 5. Okay, here's another example. Let's say we want to calculate this one, the integral from 4 to 12 of 2 over x dx. So we got the integral from 4 to 12 of 2 over x dx. And in this case here, that 2 is a constant. I can pull the 2 out in front. of the integral sign, so it'll be 2 times the integral from 4 to 12 of 1 over x dx. And if you recall back in section 5.1 and 5.2, when we were dealing with the integrals like this one, the integral of 1 over x dx is going to be the natural log of the absolute value of x. So let's bring over the 2, integrate 1 over x dx. It'll be the natural log of the absolute value of x. And this will be from 4 to 12. So now we got the upper limit minus the lower limit. So in this case here, I'm going to bring down the 2. And I'm just going to focus on ln of x from 4 to 12. So the upper limit will be 12. So it'll be ln of 12, or the ln of the absolute value of 12, which is 12. And I don't need to write the absolute value because I can take the absolute value of 12, which is 12, minus ln of the absolute value of 4, which is just going to be 4. Keep in mind, absolute value is always going to be positive. It'll never be negative. All right, there is a rule about natural logarithms. If I have ln of a minus ln of b, I can condense that using the quotient rule as ln of a divided by b. I'm going to do the same thing here. Ln of 12 minus ln of 4, that would be ln of 12 divided by 4. And then 2 times ln 12 divided by 4 will be 3. And I will go no further than that. So the integral from 4 to 12 of 2 over x dx will be 2 ln of 3. Okay. Now you might need to check back with some of the videos in chapter 1 when we were talking about logarithms. And we talked about one of these properties here. The difference of their natural logarithms can be condensed as a natural log of the quotient using the quotient rule. Okay. Let's say we got the integral from 7 to 8 of 1 over x squared dx. The integral from 7 to 8 of 1 over x squared dx. Well, let's write 1 over x squared using negative exponents. So here we got the integral from 7 to 8 of x to the negative 2 dx. Here we can pull the x squared out of the denominator and change the exponent to the opposite sign. So it'll be x to the negative 2. Here we use the power rule by increasing the power by 1 and dividing it by that new power. So here in this case, I'll write the x. Negative 2 plus 1 would be negative 1, and divide that by its new exponent of negative 1. That's going to be from 7 to 8. All right, another way of writing that would be this. I'll pull the negative sign in front since I got that negative in the denominator. X to the negative 1, I'm going to write that as 1 over x to the positive 1, or just x. That's going to be from 7 to 8. So now I have the upper limit minus the lower limit. So this will be negative 1 over the upper limit, which is 8, minus, and then negative 1 over the lower limit, which is 7. And since we're subtracting the negative, that's the same as adding a positive. So I'll have negative 1/8 plus 1/7. And this we can do in the calculator. So I'll do this. Negative, and then in parentheses, 1 divided by 8, close parentheses, plus, and in parentheses, 1 divided by 7, close parentheses. Then press your math key, select number 1 for the fraction. This will be 1 over 56. So the integral from 7 to 8 of 1 over x squared dx will be 1 over 56. And that 1 over 56 represents the area of this function f of x between 7 and 8. All right, example 6. Say we got the integral from 0 to 3 of 4x cubed plus 9 dx. And he'll want to find this integral. Okay, so I'll rewrite this as the integral from 0 to 3 of 4x cubed plus 9 dx. So here I got the integral of a sum. I can write that as a sum of their individual integrals. So here, this will be the integral from 0 to 3 of 4x cubed dx plus the integral from 0 to 3 of 9 dx. And also, if I want to, I can pull the 4 out in front. So this will be 4 times the integral from 0 to 3 of x cubed dx. Plus, and I can also pull the 9 out in front of the integral from 0 to 3 of just dx. So here, I'm going to integrate this part by increasing the power by 1. So I bring the 4 over. And here, I'll increase the power by 1. So it'll be x to the 3 plus 1, which will be 4. That'll be divided by 4. And then plus the integral of dx will just be x. So I have 9x. And all of this will be from 0 to 3. So that means here, if I simplify this, the 4 is divided out, I'll be left with x to the 4th plus 9x. And this will be from 0 to 3. So now I'm going to do the upper limit minus the lower limit. So in this case here, the upper limit is 3. So this will be 3 to the 4th plus 9 times x, which is 3, minus the lower limit, which is 0. So this will be 0 to the 4th plus 9 times 0. Now, if I do this in the calculator, I get 3 raised to the 4th, and then plus 9 times 3. That's going to be 108. And all of this right here, that's going to be 0, because 0 to the 4th is 0, 9 times 0 is 0. 0 plus 0 is 0, so 108 minus 0 ends up being 108. So the integral from 0 to 3 of 4x cubed plus 9 dx will be 108. That represents the area of this function from 0 to 3, between 0 and 3, I should say. Okay, example 7. Let's say I have the integral from 1 to 4 of 4x to the negative third minus 2 dx. I'll go ahead and rewrite it. The integral from 1 to 4 of 4x to the negative 3 minus 2 dx. So I got the integral of the difference, so I can write that as the difference of the individual integrals here. So this will be the integral from 1 to 4 of 4x to the negative third dx minus the integral from 1 to 4 of 2 dx. Now here I'm going to pull the 4 out in front of the integral sign here. So this will be 4 times the integral from 1 to 4 of x to the negative third dx minus, now I'll go ahead and pull the 2 out in front. So it'll be 2 times the integral from 1 to 4 of just dx. So now let's integrate this part right here by increasing the power by 1 and dividing it by that new power. So bring the 4 over, increase the power by 1, so it'll be negative 3 plus 1, which will be x to the negative 2 over negative 2. And then minus 2 times the integral of dx will just be x. And all of this will be from 1 to 4. So if I simplify this, if I do 4 divided by negative 2, that's going to be negative 2. And I'm also going to do this. X to the negative 2, I'm going to write that using positive exponents with x squared in the denominator. So it'll be negative 2 over x squared minus 2x. And this expression would be from 1 to 4. So now we're going to do the upper limit minus the lower limit in this case. So the upper limit is 4, so I'm going to have, let's see, negative 2 over 4 squared minus 2 times 4, then minus the lower limit, which is 1, so this will be negative 2 over 1 squared minus 2 times 1. Okay. Now, 4 squared is 16, so if I have negative 2 over 16, and if I reduce that as a fraction in simplest form, it would be negative 1/8. Minus 2 times 4, which is 8. And then minus 1 squared will be 1 negative 2 divided by 1 would be negative 2 minus 2 times 1, which is 2. Now I'm going to do negative 1/8 minus 8 in the calculator. Negative 1 divided by 8 minus 8. Press the math key. Select number 1 for fraction. It'll be negative 65 over 8. Minus negative 2 minus 2 will be negative 4. And I'm going to go ahead, since I got negative 65/8 in the calculator, I'm going to go ahead and do minus negative 4, and then press the math key, select number 1. This will end up being negative 33 over 8. So that negative 33 over 8 represents the area of this function from between 1 and 4. So the integral from 1 to 4 of 4x to the negative 3 minus 2 will be negative 33 over 8. Okay, now look at example 8 on the next page. Here we got the integral from 7 to 7 of x squared minus 9x plus 3 raised to the 13th power dx. Now I'm going to rewrite this because I want you to look at this problem very carefully. And this came from the last video that I did, which was section 5.4, dealing with the definite integral. And we talked about one of the properties of definite integrals here, where, and I will go ahead and pull up this sheet that I had from the last video. And that's going to be this rule right here, rule number 1. The integral from a to a, that means that the upper limit and the lower limit are exactly the same of this function f of x dx, your answer will automatically be 0. So that means here, we don't have to do any algebra here at all, because notice your lower limit and your upper limit are exactly the same, and we're integrating this function here. So we're going to automatically get an answer of 0, and we're done with that problem. So this is going to be from number 1 of the properties of definite integrals. So you might need to refer to that last video, section 5.4, where it says here the integral from a to a of the function f of x is automatically 0. Okay. All right. We'll move on here. The evaluation of a definite integral is a two-step process. First, find an antiderivative. Then, find the change in that antiderivative. If substitution techniques are required to find the antiderivative, there are two different ways to proceed. So the first method here is to use substitution in an indefinite integral to find the antiderivative as a function of x, and then evaluate the definite integral. The second method is to do this: substitute directly into the definite integral, changing both the variable of integration and the limits of integration. Okay, so what I mean by that is I'm going to do this in both methods in example 9. So that way you'll see what I'm talking about here. In example 9, we're going to evaluate the integral from 0 to 5 of e to the 3x dx. Okay. So here I'm going to give you method number 1. So we know we're going to have to use an appropriate u substitution. So in this case here, we're going to let u equal to the exponent for the e. That's 3x. That would mean du then would be equal to the derivative of 3x would just be 3. And then we tack on the dx. Okay. So again, you might need to refer to section 5.2 when we talked about integration by substitution, because that's what we're doing here in this example. Now, I do have the dx, but I don't have a 3. So if I want this to be dx by itself, if I want to get dx by itself, I have to divide both sides by 3. So that means dx then would be equal to 1/3 du. And now we use our appropriate u substitution here in this problem. So this would be the integral from 0 to 5 of e that to the 3x. That 3x would be our u, so the e to the u. Dx is going to be that 1/3 du. So here we're just using the substitution here. Substituting dx with 1/3 du, substituting 3x with the u. Now that 1/3 is a constant, I can pull that on the outside. So it'll be the integral 1/3 times the integral from 0 to 5 of e to the u du. And then the integral of e to the u du would just be e to the u. That's the simplest integral to take. So the 1/3 e to the u. And this is going to be from 0 to 5, but my limits are in terms of x. So that means I need to do the back substitution, replace that u with that 3x, because this has to be in terms of x. So it'll be 1/3 e to the 3x. This is from 0 to 5. And then the 1/3, I'm just going to do this. Focus on e to the 3x with these limits from 0 to 5. It'll be the upper limit minus the lower limit. So it'll be in the bracket e to the 3 times 5 minus e to the 3 times 0. Well, e to the 3 times 5, that's going to be 15. So it'll be e to the 15th. Minus 3 times 0 is 0, so it'll be e to the 0. And e to the 0 power is automatically going to be 1. So this will be 1/3 times e to the 15th minus 1. And they're going to want this in the form of a decimal. So let's see, e to the 15th would be second and ln on the calculator, then 15, right arrow, minus 1. That'd be this amount, but then I have to multiply that by 1/3. This is what I come up with, 1,089,612.124. Okay. So what I did was the first method, just go ahead and do the integration, back substitute, and then just evaluate the definite integral. Here's method number 2. Here's method number 2. Since we let u equal 3x, let's go ahead and change the limits of integration. Because we got x equals 0, that's our lower limit, and then x equals 5, that's our upper limit. Well, if we let u equal 3x and x equals 0, that would mean that u would be equal to 3 times 0, which is 0. And if x is equal to 5, that would mean u is equal to 3 times 5, which is 15. So our new limits are going to be from 0 to 15. And of course, du is still going to be 3x, 3dx, but of course, dx will have to be 1/3 du. So now, instead of going from 0 to 5, we're going to be going from 0 to 15. E to the u times 1/3 du. That's the same thing that I did up here. So here, 1/3 times the integral of 0 to 15 of e to the u du. Bring up the 1/3, integrate e to the u du. That would just be e to the u. And this time is going to be from 0 to 15. Okay, because these limits are now for u. The limits that we had here from 0 to 5 were in terms of x. So now we can do 1/3 times, in parentheses, I'm going to do e to the upper limit, which is 15, minus e to the lower limit, which is 0. And e to the 0 is 1, so I have 1/3 times the quantity e to the 15 minus 1. Well, that right there is the same as this right here. And if I did that in the calculator, I'd still get 1,089,672.124. Okay, so you do have a choice here. You can go ahead and use the substitution in the indefinite integral to find that antiderivative in terms of x and then evaluate that definite integral, or change the variable of integration and your limits of integration. Okay, so you have those two choices here. Okay, let's look at this example here. In this case, we got the integral from 0 to 1 of 9x times the quantity x squared minus 1 raised to the 12th dx. Now, in this problem, I'm going to go ahead and change my limits of integration here. All right. And I'll go ahead and rewrite this problem as the integral from 0 to 1 of 9x times x squared minus 1 raised to the 12th dx. That 9, I can pull that out in front. So it'd be 9 times the integral from 0 to 1 of x times x squared minus 1 raised to the 12th dx. So here's what I'm going to do. I'm going to let u equal to what's inside the parentheses here, x squared minus 1. That would mean du then will be the derivative of x squared minus 1 will be 2x, then dx. Now notice I got an x and a dx. But if I want x dx to be by itself, well, since I'm multiplying it by 2, I need to divide both sides by 2. So this will be 1/2 du is equal to x dx. And you know what I'm going to do here? I'm going to go ahead and choose to change my limits of integration from 0 to 1. I'm going to put these in terms of u. So in other words, I got x equals 0, which is a lower limit, and x equals 1, which is the upper limit. And I know that u is equal to x squared minus 1. So if x is equal to 0, that would mean that u will be equal to 0 squared minus 1, which is -1. And then for x equal 1, that will mean u will have to be 1 squared minus 1. Well, 1 squared will be 1. 1 minus 1 is 0. So my new limits in terms of u will be from -1 to 0. All right, so now I'm going to have 9 times the integral from this time -1 to 0. And then do my substitution here. That x squared minus 1, that's going to be u, and it's going to be to the 12th power times x dx, that's going to be 1/2 du. Now I can pull the 1/2 out in front of the integral sign. So that'd be 1/2 times 9 over 1, which will be 9/2 times the integral from -1 to 0 of u to the 12th du. So if I bring down the 9/2 and integrate u to the 12th by increasing the power by 1, dividing it by that new power. So it will be, in this case, 12 plus 1, which will be 13. So it'll be u to the 13th divided by 13. And this will be from -1 to 0. Now, if I multiply 9/2 times 1 over 13, I'm going to get 9 over 26 times u to the 13th from -1 to 0. And then we go ahead and evaluate. So in this case, I'm going to bring down the 926 and just concentrate on u to the 13th from -1 to 0. So this will be the upper limit, which is 0. So this will be 0 to the 13th minus the lower limit, which is -1 raised to the 13th. Zero to the 13th power, that's 0, minus a negative to an odd power will be negative, so -1 to the 13th power will be -1. So here, 926. 0 minus a -1 will be +1, so 926 times 1 will be 9 over 26. All right, so in this case here, that would be the area of this function here between 0 and 1. Okay. And sometimes it's best to do it this way so that you won't have to, you can easily get the area quicker. All right, look at example 11. All right, now in this problem, I'm not going to go ahead and change the limits of integration here in this problem. The integral from 0 to 3 of x times e to the negative x squared dx. Okay, and I'll rewrite this. X times e to the negative x squared dx. So here we need a u substitution. So I'm going to let u equal to the exponent of that e, which is negative x squared. And that would mean du would be the derivative of negative x squared would be negative 2x dx. Well, I got the x and the dx, so if I want this to be x dx, I have to divide both sides by negative 2. So this will be negative 1/2 negative 1/2 du is equal to x dx. And then from here, I'll just go ahead and do the substitution here. So I'm not going to change these limits here. You can if you want to, but I'll go ahead and do that. Well, I'll go ahead and do that. I can do that if I want to. Why not? Show you how easy this is. Well, then u be equal to negative x squared. So that means x is equal to 0. That's the lower limit, and x is equal to 3. So if x is equal to 0, that would mean that your u will be negative of 0 squared. That's just going to be 0. And then for x equal 3, that'd be negative of 3 squared. That'd be negative 9. So it's going to be from 0 to negative 9. And then, of course, this will be times e to the negative x squared. That's going to be what u is. X dx is this, that negative 1/2 du. And the negative 1/2 I can pull out in front, so it'll be negative 1/2 times the integral from 0 to negative 9 of e to the u du. So that's going to be negative 1/2 times the integral of e to the u du is e to the u. And my limits this time are going to be from 0 to negative 9. All right, so now let's go ahead and simplify this. Bring down the negative 1/2 and just focus on e to the u from 0 to 9. The upper limit is negative 9, so it'll be e to the negative 9 minus e to the lower limit, that's 0. Bring this down. That'd be negative 1/2 times the quantity e to the negative 9. E to the 0 power is going to be 1. And I'm going to do this in the calculator. So here, let me start with the e to the negative 9 first. So second, e, then negative 9, right arrow to get out of it, minus 1, close parentheses, and then times negative 1 divided by 2. And if I was to round this off to 1 decimal place, that would be 0.5. Okay. Now here I changed my limits here for u, because these are the limits for u. In the notes that I have here, I did it for x. I just kept my limits the same. Okay. So either way, you can keep your x limits the same or change them to limits that would be in terms of u. Okay, on the next page, let's say we got the integral from 45 to 53 of x times the square root of x squared minus 2025 dx. Okay. So in this case here, if I let u, and I have to do a u substitution, if I let u equal to what's underneath that radical, the square root, just x squared minus 2025, I'm just letting u be what's underneath the radical. So u will be equal to x squared minus 2025. That would mean du will have to be equal to just 2x dx. The derivative of x squared is 2x. The derivative of negative 2025 will be 0. I do have the x and the dx, so if I want x dx by itself, I need to divide both sides by 2 to get 1/2 du is equal to x dx. Also, I'm going to go ahead and change my limits of integration as well. These are for the x's. So that means here, x is equal to 45 and x is equal to 53. If x is equal to 45, so my value in terms of u, my lower limit in terms of u, would be this. U is equal to 45 squared minus 2025. So 45 squared minus 2025 would be 0. So my lower limit in terms of u would be 0. And if x is 53, then that means my upper limit in terms of u will be 53 squared minus 2025. Because again, I'm letting u equal x squared minus 2025. Now I'm substituting that x with the 53. So 53 squared minus 2025 ends up being 784. So now my new limits will be from 0 to 784. Okay, so I'm going to go up here, write this as a limit, the integral from 0 to 784, and then do my substitutions here. This would be the square root of that x squared minus 2025, that's going to be the u. X dx is this 1/2 du. So now that 1/2 can go on the outside of the integral. So it'd be 1/2 times the integral from 0 to 784 of, let's change the square root of u to u to the 1/2 power in exponential form times du. And then bring down the 1/2. U to the 1/2, if I integrate that, increase the power by 1, so it'll be u to the 1/2 plus 1, which will be 3/2. That'll be divided by that new exponent of 3/2. And this will be from 0 to 784. Now, the reciprocal of 3/2 is 2/3. So it'll be 2/3 times 1/2. If I simplify that, it will be 1/3. So I'm going to have a 1/3 here. U to the 3/2 from 0 to 784. So this would be 1/3 times. U would be replaced with that 784. So it'd be 784 raised to the 3/2 minus my lower limit, which is 0 to the 3/2. Now in the calculator, I'm going to go ahead and do 784 raised to the 3/2 power. So 784, press the hat key, and then 3 divided by 2. This will give me 21,952. 0 to any power except 0 is 0. So if I take 1/3 of 21,952, let's see, 1 divided by 3 times 21,952. This will be to 3 decimal places, 7317.33. So let me go ahead and finish this out. 1/3 of 21,952 equals approximately 7317.333. And do round to the number of decimal places as indicated in the homework for my math lab. So here I'm just rounding this final answer to 3 decimal places. Okay. All right, number 13, example 13. Here we're going to evaluate the integral from 1 to 2 of x minus 3 divided by x squared minus 6x plus 10 dx. Okay. In this case here, we need to use an appropriate u substitution. So I'm going to let u equal x squared minus 6x plus 10. Let u equal x squared minus 6x plus 10. That would mean du is equal to this. The derivative of x squared is 2x minus the derivative of 6x is 6. So it'll be du equaling to 2x minus 6 dx. Well, you don't see 2x minus 6 up there in that original problem, but let's do this. 2x minus 6 has a common factor of 2. So if I was to factor out a 2 in du, that would mean 2x divided by 2 would be just x, minus 6 divided by 2 is 3. So I can write that du as 2 times the quantity x minus 3 dx. All right, but I do have the x minus 3 dx. So if I want x minus 3 times dx by itself, I'll have to divide both sides by 2. So it'll be 1/2 du is equal to x minus 3 dx. And in this problem, I'm not going to go ahead and change my limits of integration. I'm not going to change these x limits to u limits. I'm just going to go ahead and do the direct substitution. So here, this will be the integral from 1 to 2 of x minus 3 dx is 1/2 du. So I'm substituting that. That'd be divided by x squared minus 6x plus 10. That's what u is. So the u goes in the denominator. Now, let's pull that 1/2 on the outside of the integration sign. So it'd be the integral from 1 to 2. 1/2 times the integral from 1 to 2 of, let's say, 1 over u du. Because the integral from 1 over u du is going to be the natural log of the absolute value of u. So I'm going to have 1/2 times the natural log of the absolute value of u. And this will be from 1 to 2. Now, those are my x limits, so I'm not going to go ahead and directly replace the u with the 2 and the 1. I need to back substitute here, replace that u with what is equal to x squared minus 6x plus 10. So I'm going to have 1/2 times the natural log of the absolute value of x squared minus 6x plus 10. And this will be from 1 to 2. That 1 to 2 are for my x values. Now, if I want to directly substitute those limits, then I need to change these limits from 1 to 2 to something else by replacing each x with u. Each x with the 1 in this u value and with 2 in that same u expression. All right, so now I'm going to bring down the 1/2 and just focus on that ln of x squared minus 6x plus 10 on these limits from 2 to 1. Upper limit minus the lower limit. So here, the upper limit would be ln of 6 squared minus 6 times 6 plus 10 minus the lower limit, ln of x value is 1, so it'll be 1 squared minus 6 times 1 plus 10. I'm going to bring down the 1/2. And this will be times the natural log of, let's see here. Let's find out what 6 squared minus 6 times 6 plus 10 will be. So 6 squared minus 6 times 6 plus 10. That would just be 10. So I have ln of 10. Hold on. Where am I getting 6 from? This should be 2. The upper limit is 2. So it's 2 squared minus 6 times 2 minus 10. That is a big mistake that I'm making here. Upper limit is 2, so it's 2 squared minus 6 times 2. So let me try that again. 2 squared minus 6 times 2 plus 10. That would be ln of 2. Minus, and I know I'm going to have ln here, so let's do 1 squared minus 6 times 1 plus 10. That's going to be 5. Now, let's go ahead and do 1/2. So that's going to be in parentheses 1 divided by 2, and then left parentheses ln of 2, close parentheses, minus ln 5, close parentheses, and then I'm going to close it again. If I was to round that off to 3 decimal places, this will be, in this case, negative 0.458. Okay. And let me correct this, because this is supposed to be a 2. Okay. All right, and finally, example number 14. Is an application problem that deals with the Fundamental Theorem of Calculus. A company manufactures mountain bikes. The research department produced the marginal cost function C prime of x equals 300 minus x over 3. And my x is going to be from 0 to 900 inclusive, where C prime of x is in dollars and x is the number of bikes produced per month. Compute the increase in cost going from a production level of 450 bikes per month to 600 bikes per month. Set up a definite integral and evaluate it. Okay, so in this case here, we're going to be finding out what that increase in cost. So we need to know what C of x is going to be, because that's going to be the integral of our C prime of x dx. Now we're going from a production level of 450 bikes to 600 bikes. That's going to be our limits here, from 450 to 600. 450 will be your lower limit, and 600 will be your upper limit. And C prime of x is 300 minus x over 3. So that means I'm going to have the integral from 450 to 600. C prime of x, that's going to be that 300 minus x over 3 dx. All right, so now if I have an integral of a difference, that's going to be the integral of a difference, that's going to be the difference of their individual integrals. So this is what I'm going to have. And I'm going to pull the 300 in front, because that's going to be the integral of 450, from 450 to 600 of just dx minus x over 3 has 1/3 in it. So I'm going to pull the 1/3 out in front. So it'll be 1/3 times the integral of x dx. And that's going to be from 450 to 600 as well. So now the integral of dx is just going to be x. So I'm going to have 300 x minus 1/3. The integral of x, we increase the power by 1, so it'll be x squared divided by that new exponent of 2. And all of this will be from 450 to 600. So if I simplify this a bit, I'm going to have 300x minus 1/3 times a half will be 1/6 x squared from 450 to 600. So now we're going to do the upper limit minus the lower limit here in this case. So my upper limit is 600. So I'm going to have 300 times 600 minus 1/6 times 600 squared. And then minus the lower limit. I'll replace each x with that lower limit. So it'll be 300 times 450 minus 1/6 times 450. And that's squared. So here I'm going to focus on this part right here, the first part, and then minus the other part. This can be done in the calculator. So I'm going to have, let's see, in parentheses, 300 times 600 minus, I'm going to do this as 600 and then square it, and then it'll be divided by 6, because 1/6 is like dividing whatever I get by 6. That's going to be 120,000. So this part, this first part right here is 120,000. Then I have to minus whatever this is. So in this case here, I'm going to put this in parentheses, 300 times 450 minus, I'm going to do 450 and square that, divide that by 6. That'll be 101,250. So I got 120,000 minus 101,250. So if I subtract 120,000 minus 101,250, I would end up with $18,750. So in this case, the increase in cost going from a production level of 450 bikes per month to 600 bikes per month, that increase in cost would be $18,750. Okay. All right, so that does conclude this video in section 5.5 dealing with the fundamental theorem of calculus. Feel free to reach out to me if you have any questions about anything that was presented in this video, or if you have questions about the homework that's in my math lab for this section.